Yeah, it's about noon now. Thank you so much for these wonderful talks. I think that's been a very high standard of talks here. There was a question that
you all want
what
switch on the content, right?
What?
No, there's the dialog box. Content isn't visible to everyone yet.
Oh, okay. Bring it on screen. Okay. I think it's okay, right? Isn't it? I think it should be visible to everyone. Is it not?
No, I think you need to switch that.
What? Okay, I think it should be fine. Okay, so this is a question. Well, I guess we're already kind of doing this, but I'll just ask this question anyway, which is about using AI to prove so far unproved theorems. There was a lot of talk about auto-formalization, and what about proving theorems that we haven't seen before? Does anyone want to start? So we'll open it up. I don't know. I'll open it up to the panel. Who wants to start?
I mean, it hasn't really been, we haven't seen this at scale yet, right?
Yeah.
So, you know, it's, as a mathematician, it's not, you know, that's not a question I'm thinking about, but I'm sure the tech companies are thinking about it very hard. But, you know, we've seen AI solving Erdős problems, which turned out to be simple. Let's put it that way. And we've seen AI helping humans, and in my mind, that's much more interesting. But we've seen little of AI autonomously doing things that seemed completely impossible. But, you know, times will change, perhaps.
Thank you. Anyone to add to that?
I'm not a mathematician, and I don't see AI as being creative. I think it's very good at noticing when something is similar to something else, possibly in a way that a human being might not notice, and that might lead to a proof of something because of this analogy. But I always say, like, what is mathematics really? It's who had the idea that conic sections were an interesting thing to study like 3,000 years ago? Where did that come from? And could a language model say, right, this particular weird thing is the thing we should study next? I don't think it can do that.
I mean, I could talk and talk and talk about. I mean, does Paola want to say anything? I could fill the space provided with the answer to this question, but I'm not entirely sure that's welcome.
No, I just wanted to add, it depends what we intend as a community proof to do, because if we just want proof if you just want proof to be a mechanism for verification, then maybe, I don't know, I'm not a mathematician, but what I've seen so far, even in the proof that have been produced for known theorems, there is a lot of the other things that we would like proof to do that they're missing. I mean, when the first 2 years ago came out that some generative AI system had solved the Olympia problems to get the silver medal, and then everybody got excited, and then it turned out that these were lines and lines and lines of lean code that nobody could read and nobody could understand, and then I don't really know that I want to call that a proof, right? In the sense that yes, maybe it verifies and maybe this thing is correct, but it's not telling me anything about how things work, or I don't really understand anything about the structure where this belongs to.
One of the proofs started by doing induction on 10. Did you see this?
No, I didn't do that.
Induction on 10, but it was induction on 12. And,
okay.
And I had to think really hard about what that meant. I had to like fire up the code and try and work out what happens if you've got this thing you want to prove, and then you start by saying, okay, now let's do induction on 12. Yeah. And it's because it turned out to be sort of legally valid thing to say. But of course, I mean, you know, at the back of your mind, it's not going to be very useful.
Yeah.
But
I have really been surprised at how natural the proofs were that I was getting out of Claude.
This was 2 years ago. We were doing induction on 12.
Yeah, but this is well-known mathematics. I think Claude is maybe driven partly by Hall light, partly by its innate knowledge. And as I said, the main issue is it makes often very long-winded proofs of things that have simple proofs.
you think that will change?
I think anyone who makes predictions in this time is an idiot.
Correct.
Okay, so there are no more questions on the Q&A, but perhaps I'll ask a question. I think Larry gave a good response to one of the questions that was asked earlier, essentially in his talk, about what is it to give a proof, and it's not maybe just having some auto-formalized bunch of incomprehensible stuff. I don't know, does anyone else, any of the other speakers, have any thoughts about that? If you have an auto-formalized proof that no one has read, is that a proof?
I mean, the formalist to me wants to say, sure, by definition. But yeah,
this is a tree falling in the forest kind of question.
Yeah, it's
yeah, but if you just think about proofs as formalization and kind of just showing that something is true, then from an educational perspective, we fall into this trap that then students don't care about what they write, because nobody, it's just enough that that this is correct and nobody needs to read it. And so you have this communication kind of role of proofs that dies down by the wayside. And when you start to say students, well, actually, you maybe also should put some words in your proofs. They look at you and they say, why?
Yeah, but it's not really the right question. Somehow, is it a proof? And the question is, what does humanity want? That's the right question.
Exactly. I mean, I don't think that okay, so I'm gonna say something. I don't think that there is somewhere outside the community of mathematics and kind of absolute idea what a proof is. What a proof is defined by the community of mathematicians. I think that we agree in that. So it depends what we want a proof to do.
I really think AI should be seen as an assistant, not a replacement. It is so useful. I recently did a big project, which was this diagonal Ramsey thing, which was very much at the edge of things I understood, and which I had to ask, like mathematics undergraduates, what the hell does this mean? What does that mean? And there, it would have been so useful just to have a language model. I could have asked it, and these were all very routine questions that it surely could have given very lengthy explanations. Helped me a lot. Would have helped me a lot if I'd had it, instead of having to hunt down someone like Mantis Baxis and saying, what are they doing here? And imagine if you have this by your side, because in math, one striking feature of mathematics is how you think you're working in one world and then suddenly you're way out there doing something that you don't know anything about. And either, okay, you can go down the corridor and ask the other guy if he's in his office and see what's going on, how do I do this? But if you had something that had, again, all this is mostly basic knowledge. I need to know this weird fact in combinatorics. How does that work? And it will just know the answer and tell you. I'm sure that will help people do their own work and get it done more quickly.
Yeah, as I say, this term I gave these talks on Fermat's last theorem, just regular maths talks. And I just found that just reading the literature, people would just say, oh, now, and now, the other cases are clear, or things like this. And you could absolutely just ask, just here's the statement, just can you fill in all the details, please? Save me the trouble of having to generate them. And it's extremely good at reading 30-year-old or 20-year-old papers, saying, yeah. And I should say it's also not perfect. Sometimes it was, oh, it's doing this, this, and this. And I'd read it and think, no, it's not, because that doesn't work. Like, well, what about this counterexample? And, it would be a dialogue. I had the advantage that I was already an expert, but I wanted to move quicker. And there, it was a perfect tool. I've got this lecture on Thursday. I need to understand this stuff now. And there are these, I've read it carefully, but there are 3 bits I can't quite immediately get. How do these work? And one of them, it just taught nonsense. You'll say, no, that's not right. And then have another go until we get there together. But yeah, and I imagine that this is how the smart students are using them as well.
Yeah, I mean, that is something that I don't quite know how to reconcile, because we want students to learn how to use these tools, because obviously, as you were saying, they are incredibly useful, but the way in which you learn these tools are from a perspective of an expert. I want my first year mathematician first to become an expert and then to be able to use this tool to make their work more quickly. And I'm not quite clear how we can reconcile wanting the students to learn this tool, but also wanting them to know enough mathematics so that they can be experts and they can use them reasonably, right? This is really not very clear to me yet.
Great. So we've got some interesting questions in the chat. So first question I've got is that Larry mentioned that higher level features of maths, for example, aspects of foundations, are sometimes not available in a proof tool. I wonder what the panel thinks about whether there are certain areas of mathematics that are in general less amenable to formalization. For example, perhaps areas requiring more conceptual or intuitive moves.
I mean, one obvious answer is that if you're working in foundations, then you're fighting against. If you're trying to do foundation X in a theorem prover that's built on foundation Y, then you're constantly fighting the system. That's something. So some people come along and say, oh, they want to prove that this is equivalent to the axiom of choice, and I'm just like, you know, if you try that in lean, it's a bit terrifying because a lot of lean's tactics just assume the axiom of choice without thinking. It's just sort of the way the system's built, and so you are fighting the system then. But when it comes to mathematics that isn't, you know, foundations, I don't see. I'm less convinced. I mean, if some mathematics is harder to formalize, it just means it's just less formal. I mean, it's not sort of system. You know, if it's more pictorial, then you're going to have to explain more carefully what you're talking about. But yeah, that's just so that. I mean, in my mind, that's just what mathematics is. You know, if you say mathematics is formal strings of symbols, which a proof is what it thinks it is, then unfortunately you do have to translate geometric pictures into formal strings of symbols. You know, in my mind, that's fine.
I don't think mathematics is formal strings of symbols. I mentioned in my talk about a counterexample to a particular Ramsey claim that consisted of a graph, a particular counterexample. It's in graphical form, and you want the computer to read the graph and to check for the absence of the cliques, which if the graph is large enough, it would take a long time. And then you think, well, is there maybe a fancy algorithm that would do it? And then do you have to formalize the algorithm, prove the algorithm is correct, and somehow link up the algorithm with this thing? It is unfortunately the case that very often the thing that is obviously true is not so easy to prove, and often for a dumb reason. So it's not like the Jordan curve theorem. So what does the Jordan curve theorem says? Every closed curve divides a plane into two inside and an outside. And that's maybe not a good example because I believe a proper proof of the Jordan curve theorem really is very technical, and that is unavoidable. So that is not the kind of example I mean. But when you do a thing where you do two constructions and they are obviously isomorphic or obviously have the same cardinality, and yet sometimes it's a pain getting your system to do this, to prove it formally. And this is, I think, the reason why a lot of people just lose patience.
I think your Ramsey example was quite. If memory serves, the way you prove that R36 is bigger than 17 is you simply write down a coloring of the edges of a K17 to do with whether the difference is a quadratic
and the coloring is even given. The coloring is even given.
Right.
So all you have to do is check it.
But I think the coloring can be defined by a relatively straightforward algorithm, and the proof that there's no triangle, I think you can do conceptually.
Well, you could see it with your eyes, but can the computer see it?
Yeah, sure. But then the proof that there's no blue K6. I think this is just a case of enumeration. But of course, computers are good at that, right? 17 choose 6 is not a big number nowadays, and you just check them all.
Well, yeah, but if the graph gets bigger,
Yeah, sure. But like our knowledge of Ramsey numbers doesn't extend much further. So
No.
it's not, in that case,
No.
it's not going to get much bigger.
But it's an example, I think, of the variety of different things. So if you looked at that particular paper, you have on the one hand this thing which is just a graph and just checking and enumerating a picture, and on the other hand, some very detailed argumentation about, about edges and vertices in a graph where you make all these different constructions, which, as I said, I probably could have got through Claude in the end, but I frankly lost patience with it. But that was just a technical proof, so I guess that's not what we're talking about here.
Okay, brilliant. I know, Paola, do you have anything to add on that point? If not, okay. So then we've got first of our religious debates. It says we've had a mention of Lean and Isabel. To a mathematician interested in getting involved in formalization of standard mathematics, this feels a bit like VHS versus Betamax. Is this unreasonable? Lean seems to have a lot of momentum behind it, in part due to Kevin's efforts. Is there a case to be made that for the purpose of formalizing mainstream maths, we should get behind a system and start using it, despite its drawbacks, in much the same way that everyone has accepted LaTeX? Or will this become irrelevant as it becomes easier to use auto-formalization tools to translate between systems?
Paola spoke about 6 systems at some point.
Well, yes, I mean, there are the ones that are really only considered for teaching and made up for teaching, but there is a lot of kind of theorem provers. I mean, I don't know. I mean, from the viewpoint of formalization, I don't really know, but from the viewpoint of education, it means it depends on what you want to do with the systems, because different systems have different capabilities and different possibilities, and that can enhance different mathematics capabilities in the students. So this is why some work on trying to understand how the system performs on tasks that you would maybe want to do to mathematics students could be interesting. But this is from the viewpoint of teaching and learning, not so much from the viewpoint of formalization of mathematics.
I think people have to be rational here. So clearly, if you want to do a project and everything you need is already in MATLib, and is not in Isabelle, I would be pretty dumb to say, oh, you need to formalize all that stuff in Isabelle and then do it in Isabelle. That's just not being reasonable. I think people shouldn't overlook Isabelle for a project they're doing where, in fact, the library situation is not so overwhelmingly in favor of Lean here. A thing that bugs me is people sometimes underestimate the progress that has been done even way back. So Automath came out in 1968 and arguably already had almost all the ingredients needed to formalize mathematics. The two big drawbacks of Automath were its syntax, was really uniquely horrible, and there was no automation whatever. But if one can ignore that, and a lot of people ignore some pretty awful syntax, I think there is very few limits to how far you could go, even in Automath. By about 1975, they had formalized the book by Landau, which was mostly elementary stuff, but the Dedekind completeness of the reals is not a completely trivial theorem. So that was done in 1975. By 1985, we had Gödel's first incompleteness theorem formalized using Boyer-Moore, and quadratic reciprocity was also done in Boyer-Moore in the late 80s, maybe. So a lot of people have been doing this, in fact, for a long time. And when you sometimes read a thing on Quanta or whatever, they tend to overlook all of that. And I do feel, I knew a lot of these people. Their work deserves some credit. And of course, a huge amount of stuff done at Hall Light by John Harrison. The formalization of complex analysis in the, I guess, early 2000s or something. That was also a good achievement.
My views on this have changed slightly. I think a few years ago, I was absolutely adamant that it was clearly best in everyone's interest if one system won. Because it would just, you know, because then we'd all be talking the same language. But now, given that it seems, I mean, Larry's talk, you know, Larry's like, oh, you know, I've got this theorem in Lean and I tried to translate it into Isabelle, and, you know, machines can do that kind of thing. You're just kind of thinking, maybe sort of under the hood, maybe it doesn't matter anymore. I mean, I think it's great that Lean has got this gigantic focused maths library with one definition of everything. I think that definitely plays an important role. But if the systems are going to become interoperable, then maybe it doesn't even matter which one wins.
It is a great
there's
thing,
no
actually.
notion of winning.
Yeah.
Sorry?
Yeah, I mean, if your guy who wanted to do the proof needed these certain mathlib entries but wanted to use Isabelle, he can say, okay, set aside a couple of hours to translate those and then do it in Isabelle if you want, you know. I do wish I knew someone who understood martingale so that they could look and just check that it did it right, because I haven't the faintest.
There are people at your university that understand martingales very well. In fact, one of them taught me martingales.
I just wanted to add that there is another dimension to this conversation, is that the hardware is developed since the 60s in such a way that now every student has a laptop on a desk. This wasn't the case in the 60s, and this is the case very often, that technology develops much earlier than they then become available to everybody. And I think that this is what's happened with theory improvers as well. What's happened in general with a lot of the technology that is used in university. And I think that this is why Canvas is taken off at exactly this moment. Is a little bit what happened with kind of pocket calculators and graphic calculators in beginning of the 2000s. All these things existed before, but suddenly your students in high school could have one in their pocket, and then the situation suddenly is different. And I think with your improvers, it's a little bit the same.
Thank you. We have another question. How far are we from having AI systems to help review research papers in maths, with or without auto-formalization? What are the most major challenges?
This could be tried today, right? People they upload their things in LaTeX, right? The experience shows that LaTeX is better than PDF, but all the archive things are in LaTeX. Got the source. You talk to Joseph nicely, maybe give him some money so he can buy more AWS credits, and let him feed his thing into it and see how far he gets. That might be interesting. It may not work for, as you've always pointing out, Kevin, a lot of maths rest on these gigantic hierarchies of definitions that are not available, in which case it's not going to work. But at least like these Ramsey things I've seen, they don't require any advanced definitions. I think you could feed one of them into an LLM very quickly and see what it thinks.
Well, I think we should auto-formal. I mean, people are doing that already, right? Asking LLMs. This is the irony. You get these LLMs proving, quotes, new theorems, and then the AI researcher decides to check it by asking another LLM if the proof is correct. It's just like, I don't know. There's something slightly farcical about this. But auto-formalization, I think we're at the point now where it will work for some papers, and it won't work for others. We're at a sort of a funny time where it'll work for some things and it won't work for other things. And maybe in a few years' time, it'll just work for everything. But I don't see why we can't auto-formalize a paper if all the basic definitions are already there or are really very easy to state. The issue is people proving fancy things in the Langlands philosophy, where none of the systems can even understand the question. Those we're not ready for yet. But who knows where we'll be in 2 years' time.
But also, when I don't review mathematics papers, okay? I did a journal in mathematics education, and for social sciences, that conversation is quite different. But when you review mathematics papers, surely you don't just check for correctness.
No, that's just one of the. In fact, you don't check for correctness. That's not the referee's job.
Yeah, exactly. So there is a lot of studies that have been done regarding this reviewing process. So what your LLM could do at best could be, I put this theorem in Lean, and Lean tells me it's correct. But that is only one part of the reviewing process. I imagine there will be a lot of other things that come into being, right?
Am I the only mathematician on the? I suppose Larry's probably a computer scientist. and you call yourself an education specialist.
Yep.
But one of the nice things about checking to see if a proof is correct or not is if you can find a counterexample to the main theorem, then the papers are very easy reject. That's the thing. So it saves you the bother of having to do all the other complicated things, which is trying to work out if the techniques are interesting and if the result is increment. I mean, the questions you have to answer depend on the caliber of the journal as well.
Yeah, of course.
But yeah, and you do have to do a lot of things that no way can a machine do. Not yet anyway, and possibly not ever. But yeah, checking correctness is just, it's an interesting. I mean, it would be useful if we had a thing that could check that. I mean, given that my understanding is that journals are about to be sort of swamped by AI slop papers. And I heard a talk by somebody from Archive a week or so ago, and I thought that the main culprits were going to be cranks, but they say that actually that a big source of the problem is currently undergraduates from serious institutions who want to bolster their CV by saying, "Oh, I've got a paper up on Archive." So they get LLM to generate a random paper, and then they submit it to Archive, and then Archive have got to, decide if this is absolute nonsense or not. And the person submitting it might well have an academic email address from a prestigious institution, but this is, it's only a matter of time before the journals start being swamped by these things. And so if you do have some kind of system that can at least, but it's so ridiculous. It's such a ridiculous, we say, if the journal then pays money to prove that this result is rubbish, whereas the person writing it has then also paid money. And the whole thing seems like some gigantic pyramid scheme, doesn't it? Mm. No, there is a role in there's definitely it's definitely useful to be able to check if a result's correct, but we're not there yet. But in a couple of years we might be. But yeah, that's definitely not everything.
Okay, thanks. We've got a question about the ethics of using LLMs. How do you view the ethics of using LLMs, environmental costs, the question of intellectual property, the exploitation of human labor during training? Any thoughts on that? Yes.
One thing that I've certainly noticed, this is not something that gets talked about a lot, but somehow you ask an LLM how to solve a problem, and a maths problem, and the LLM tells you how to solve the problem, and then you go around saying, "Oh, the LLM told me," but what's actually happened is that some person told you, an expert told you, and the LLM is just telling you what the expert wrote on the internet, and you don't know who the expert is, and the LLM probably doesn't know who the expert is either. And I've become increasingly, my first reaction when I started using these tools was, "Oh, this is great. This is like telling me how to do stuff." And I'm like, wait a minute, this is actually it's communicating ideas that other humans are having, and I'm not crediting these humans at all. So I'm saying, "Oh, thank you very much to the tech companies for making this tool." But really, the humans are sort of missing out here. So that's something that upsets me a little bit. And you don't know who to credit. You say, "Oh, the language model told me," but whose idea it was, I have no idea. It certainly wasn't the language models. So
it's really interesting. So in a lot of studies done with students, with higher education students, and in particular with mathematics students, about what they think about generative AI, it comes out that these worries about ethics and sustainability are really, really a big factor. So this come out of all the studies, and I'm just writing up a study where we pulled 850 students across Finland and the UK. And again, this comes out: ethics, sustainability, where the data come from. Do I have a kind of a permission to use? How do I acknowledge the person? But the students are kind of in the middle between having all these thoughts about whether they can really use this tool and what are the ethics connected, but also things like, is this tool kind of degraded my critical thinking because it does my thinking for me, and seeing that they are entering a work market that will require them to be able to use these tools. And so there is really quite a bit of friction here, because on the one hand, a lot of students are a bit kind of thinking, well, I'm not really sure I want to be part of this game for a lot of reasons, but then I have to engage with it because when I enter an office next year, I will be asked to use these tools, or the company tools equivalent, and so on, which is also quite an interesting thing to see. And as universities, I don't really know what is possible to do. A lot of students ask for some sort of training, but I don't know what sort of training you could use to use generative AI responsibly.
It's not just that they're going to enter, the workplace in a couple of years' time, and so they'll better need to know the tools by then. They're seeing that their peers are using the tools, and their peers, they're competing against their peers in some sense. That's one way you can think about a degree, right? You're all trying to get the highest mark,
although I think that from the studies that have been done, I think that so university have always had a pot of students that will do anything to get a high mark, right? So for us in the social science, there's been essay meals. I mean, essay meals have existed for a lot of time, and there are cheaper ones and more expensive ones. And now suddenly we have generative AI, which is another tool. 4 years ago, 5 years ago, the paid version of Wolfram Alpha could do any paper that I could set to my electronical engineers, right? Because that's how it is. So there will always be a common number of students that will do anything to get a high mark. But I don't think that there is this kind of much greater influx than my colleagues think there is. Right, so I don't think that suddenly with the advent of generative AI, the number of students asking generative AI to do the coursework is spiked to the ceiling. I don't really think that that's the case.
Thinking about ethics and AI, in general, there are a lot of ethical questions about LLMs, but I don't think they're particularly relevant to us. When I think of using LLMs to formalize mathematics, I don't generally think I'm stealing other people's labor because I contributed so many of those libraries myself. So to me, it feels more like I'm multiplying my own labor, and that seems fine. Now, okay, it will have absorbed. I mentioned in my talk how I had asked it to prove a thing for which it needed some group theory concepts that hadn't been formalized, and it just formalized them. So it had clearly absorbed some group theory textbooks and just dumped out these definitions and then proved the key property. And okay, so you could argue it stole something from an author of the book, and indeed there are many aspects of the way these LLM rows behave, which is deeply disturbing. I think Sam Altman was certainly been described as a sociopath. But I think for the specific thing of formalizing mathematics, we're not putting people out of business, right? It's not like kids will go hungry because daddy can no longer make his salary formalizing mathematics, because no one ever made any money doing that. On the contrary, we are making it possible to bring a higher degree of security to things that were before had to be taken for granted. So in a sense, in here, we're actually applying AI to something that is constructive as opposed to so many of the other applications, which are at best neutral, if not actually destructive.
Thank you. So I'll ask a maths education question. So I know, Paola, you were saying you're kind of moving away a little bit from the transition. And that's perhaps because, yes, it's very hard for someone to start using Lean at the undergraduate level, if that's their first, or any other theorem prover at the undergraduate level. But let's suppose we imagine a world where students at secondary school are using interactive theorem provers, and so they already know how to use them. So here's the question, I guess, to the panel, which is, what would a first-year undergraduate mathematics experience look like in a world where students are already happy with using some interactive theorem prover?
Can I question the premise?
Okay, yeah, you can question the premise.
These things at school, we're not really teaching people proof.
Yeah.
And these interactive theorem provers, kind of proof is the strong point.
Yeah.
And so I can't quite see a world,
I'm having a fantasy. This is my fantasy world.
then
So it's your-
then that's great. Then we can just dump the intro to proof class because then us all understand proof already.
Okay.
Yeah.
What exactly? I would love to get, interactive theorem provers into schools, but I don't see. My vision at some point was, what are the proofs that you learn at school? You learn these geometry proofs, right? Triangle theorems and circle theorems. My children were all dragged through these things, and they're sort of dressed up as calculations. It was like, if this angle's 20 degrees, then work out this angle. But they're not really. They are proofs. Like, if this angle is X degrees, then you're working out this angle by doing some calculation by applying theorem after theorem, which says how this angle is related to that angle. And I thought it would be great to have some kind of lean powered game where you do all of this Euclid stuff and you do it all properly and lean checks it all. But that somehow these games already exist, right? There's this game Euclidia, used to be called Euclid the game, and you don't need lean to do that. If you want people to do Euclidean geometry rigorously, then you can just make your own standalone app that does that. So I can't work out how to get lean. I mean, obviously there'll be, bright school kids that are doing things off syllabus, but most school kids have got other things to do.
I think that, the premises is that maybe the school curriculum should include a little bit more pure mathematics than it does at the moment. And then when there would be a little bit more proofs, then maybe one could think about using lean. The issue with the transition is that this is not there. Students come to university and they think they've joined the wrong degree because they don't recognize mathematics with what they have seen before, right? And this is why there is all this
What's the
emphasis.
method? I've been
Exactly.
asked.
Huh?
What's the method?
Yeah.
In
So
this intro
this
to
is
proof class,
why-
it was like Gödel said there's no method.
So this is why people design transition to proof courses. So we've just designed one at the University of Edinburgh, which we run for the first semester this academic year. And it's all about trying to get the students to understand the mathematics, not the mathematics, but what is the mathematics that we're doing at the university and how is that different? And we're trying to play on this idea of proof, on all the roles of proof and like the verification, the communication and all that kind of stuff. So, but if this happens in school,
I blame Sherlock Holmes because he always says he's doing things by deduction, but he almost never is. So he's usually using abduction or induction. There's very little deduction. And when ordinary people have no idea what deduction is, and again, this is kind of verging on philosophy of mathematics or something, but it's not impossible to teach, I think, a teenager. Well, I think teaching them what the other things are much more easy. So abduction, as in if a certain person has mud on their shoes, fresh mud on their shoes, then they were previously in a muddy place, and that is abduction. And that is a kind of reasoning, and people, I think, if they understood that is one form of reasoning, but there is another form of reasoning where you have assumptions, and then you have certain ways of making a conjunction or something. I mean, most people struggle with the concept of a contrapositive. And I think this is actually knowledge everyone should know. I think an ordinary man or woman in the street should know that if A implies B, then in fact, if you know not B, then definitely not A, because, people should not struggle with such a simple
but that's
thing.
more,
And that could be...
but that's really complex. So there's a lot of psychology studies that have looked at whether the logic and the kind of way of thinking that you acquire by doing mathematics degrees impact on context outside of mathematics. So, for example, they use these tasks where you have 5 cards and then you have maybe a D over a card and a 3 over another card, and you have a set of rules. And so if you have this one, you don't have that one, blah, blah, blah. And so they give this. And mathematicians don't do any better. I mean, the context is really important. So even if you know these things from doing mathematics or from doing truth tables, they don't make you a lot better at thinking in different contexts from mathematics. I mean, there's a colleague of mine at Loughborough University that's been studying this for a very long time. And this is what is really interesting, is this idea that these are not, knowing these things doesn't give you an absolute capacity of reasoning in any context in a more logic way. It really doesn't.
System 1 and System 2 effects, as they say.
For
You
example,
know, the System 1 where you jump to conclusions without really thinking.
but
The
even if you
humans
are in a
use. Sorry, go on.
No, you go. So
I
even
was
if you
just gonna-
use situations that there is no intuition, right? Because if you have a game of cards, what intuition is that, right?
I
Do
don't
people
know.
have a good understanding of logical implication? You know, you think everyone should know the contrapositive. It's not entirely clear to me that people know the difference between P implies Q and not P. When you say things like, if you don't get down from that tree, I'm calling the police. But that doesn't mean.
Well, that's more of a threat.
But what that really means is if you do get down from the tree, then I'm not going to call the police, right?
Yeah.
Somehow it does mean.
True.
It's an if and only if. You don't say it. But what you're actually saying is you get down from that tree and then I won't call the police, which is almost, it is not the same as the words that come out your mouth.
No.
So, going back to school kids, the initially I got interested in theorem provers because I was given Imperial's Intro to Proof class to teach by Martin Liebeck, and I thought it would be really interesting to jazz it up and introduce some technology. And that was my initial vision for the system, as I think Paola is well aware. It's like you show weak students how to use theorem provers, and then suddenly they'll understand proof much better. And the reality was completely different and nothing like my
The weak
ridiculous
students
and wrong
couldn't
idea.
cope.
But yeah, it turns out that giving a complicated piece of software to a bunch of struggling students was not the way to make them understand proof.
I have to say, for teaching, I think Isabel would be better because I think there are certain things about any dependent type system that look distinctly weird and unintuitive. And for the kind of simple things you would be doing, or you don't have proof objects, for example, as a confusing additional thing, it might in fact be simpler pedagogically. I don't know if there's any evidence for this.
I would imagine in Cambridge they're not being used in the maths department.
No, I'm not
Are
aware.
they being used in computer science?
Not for teaching, as far as I know. We teach it to fourth-year students, I guess, but we don't use it as a way of teaching proofs. It's just teaching it as a tool for verification.
Right. So the same thing that we're doing at Imperial now, sort of this optional. Yeah. I have a question for Paola. I don't know if I'm allowed to ask a question.
I'm sure you are.
Unfortunately, I can't ask a question because my doorbell's just gone. I'll be back in 30 seconds.
Okay.
Okay, well, while Kevin's getting the doorbell, I've got a comment here from Tyler, who's a philosopher. In my experience teaching logic, there is a significant difference between learning what a given logical rule is, for example, how to define contraposition, and learning how to recognize it in any given context. I'm not sure how to teach the latter. Oh yeah, so Kevin, this is a comment that from someone who's experienced teaching logic, that there's a significant difference between teaching or learning what a given logical rule is, for example, how to define contraposition, and learning how to recognize it in any given context. And I'm not sure how to teach the latter.
Yeah. I knew how to do logic before I'd seen any logic course. Because I was just doing Maths Olympiad problems where you just pick up what you can and can't do with logic by just experimenting. When I had all the time in the world when I was 16 years old and trying to work out silly questions about the integers, which I was thoroughly enjoying doing as part of this British Maths Olympiad scene. Yeah, you just realize that you could understand how logic worked by trying a bunch of examples, and then you sort of realize what could and couldn't be done without ever seeing the abstract framework or the law of the excluded middle or anything like this. You just got some intuitive grasp about what you could do with mathematical objects based on trying examples. I remember my father taught me how to differentiate. And I thought, this is great. There's a new thing we can do. And I've I've been trying to work out how to trying and failing to solve cubic equations around that time. So I'd have like, x cubed add 3x add 7 is 0. And I think, well, how am I going to solve that equation? And I have this great idea. It's like you can differentiate both sides. So this is great. Derivative of 0 is 0. Derivative of cubic is a quadratic. So this is fabulous now. So now I've got a quadratic equation. I can solve quadratic equations. So then you solve it and you get numbers that don't work. And you're just like, wait a minute. You sort of you have to sort of try and work out, how logic works.
You'll be solving quintics next.
Yeah.
My method would have worked for all
Yeah.
then. It was great. It's just unfortunately gave the wrong answer. But yeah, you just work out things by trying and failing and experimenting. And who needs formal logic? You just get the instinct. The thing I was going to ask Paola was, we're teaching. We've just redesigned our third year lean course because the AI is at the point now where by this time next year when we're teaching it, it'll just be able to do it'll be able to write the projects for us. So we're proactively moving. And so we've just, taken people who've taught it before and said, what are your ideas? And then we put them all together and great, now we've got a new lean course. And I think you would instantly say, now, how are you going to evaluate that change? And I'm just going to be like, I've got no idea how to evaluate that change. So I was going to ask you, how does one evaluate what we're doing?
Well, it's really quite difficult because it depends on what context you do. The difficulties that we often have is that these courses are really quite small. So I don't know, how many students do you have on the lean course?
40 now.
Oh, wow.
It's
Okay.
crept up. Well, that's because it's this project-based course with no exam at the end, and people tend to get high marks for it. So people are realizing that actually it might be a good option.
Yeah, so I mean, the thing that I can think about is to collect some analytics, like, for example, are the students coming to the lectures and they are engaging in some way or another. I don't know whether you use the VLE very much or not, that collects analytics as well. And then you can see like a pattern engagement, but the bulk of the evaluation would be a qualitative evaluation. You need to talk to the students. So you need to talk to the students before and after, and maybe give them some task afterwards. They are trying to kind of understand whether they've engaged with the ideas that you wanted to do, you wanted them to get in lean. So I would think something like this with a number of that type, that's what you can do. But I think that the most important thing is not to be able to come up and say, oh, well, the course has worked because I've seen that my students can, because this is what I wanted to do, and I think that my students can do this and that. But it's try to understand the general mechanism by which you are observing that outcome, because then that's transferable, right? If you understand the context and the mechanism, then it's transferable. So then you give your thing to another person and you say, look, this is the mechanism, this was my context, how would it work in yours? And this is the only thing that is interesting, but it's difficult, as I said, with small numbers like that. So when I do evaluations of this sort, I haven't done anything with lean, I've done some stuff on oral assessment, then I'm going to go and look back at what happened in previous course, was the mark distribution, what's the mark distribution now, so you kind of gather all sorts of, but we can have a chat separately if you want.
Because I thought it's very clever. I was being ahead of the game and having a lean course, and then suddenly realizing you just got to redesign it because AI is moving so quickly.
Yeah, no, exactly.
It is unbelievable, the pace of change. The things that I showed you in my talk, I wouldn't have imagined existing even a month ago.
Yeah, a year ago they were science fiction, weren't they?
Yeah.
The other thing which is really interesting is that from this study that I mentioned before that I've done with UK and English mathematics and Finnish mathematics students, is that this was a study about their perception of general AI in their education in the future and other bits and pieces. So we collected the data at 1 year difference. So first we collected data here in the UK. This is a mostly quantitative study with a qualitative kind of thing to it. And a year later, we collected data in Finland, and we were already quite prepared to treat the two data sets as completely different data sets because of these reasons. There is no significant difference in any of the fields of the answers. And I think that for as far as our students are concerned, we have gone over the, oh my God, yesterday I have ChatGPT. I didn't have ChatGPT and today I have it, to a plateauing of perceptions and attitudes. Now they have this tool, the tool is getting better and maybe there are better things and so on, but now they have it and this is what they think, which I think is quite interesting. I mean, we're really, I mean, generally my quantitative colleagues were really surprised that they didn't see any significant difference in the answers. So this is another thing that to think a little bit about.
Okay, so we've had another question. It's for Paola mainly. It says in intro proofs courses that you have seen that used Lean or another ITP, what is typically the proportion of time spent on informal versus formal proofs?
Well, I only really looked carefully at 2 courses, but one was Kevin's course in 2018, so Kevin can tell you more about it. And the other one is the course that Heather Macbeth used to write, used to do for them. And I think that she's taken this to Imperial College now. I don't know. I worked with the colleagues that ran the course last year when she left. I mean, in that course, I think this was pretty much integrated. So I would say this is pretty much half and half. So Lean was a compulsory part of that course. The aim was to teach students to write proofs on pen and paper, and Lean was one of the things that kind of was used to encourage students to write proofs. As I said, one of the assessment was asking the students to write a proof of the same mathematical statement in Lean and on pen and paper. Right. So that was the idea. So the aim was always, I think, to get the students good at writing proofs on pen and paper and to use this tool to try to overcome some of the issues that they had. But the difficulties we are having is that there aren't a lot of courses that have Lean as a compulsory part of the teaching. So
yeah, our intro to proof class, I would give some proofs. I would do things like, look, composite of injective functions is injective. I'll show them 3 Lean proofs and say that if they didn't understand anything, then they should just read the textbook. But it was always an option in that old course.
We taught a discrete mathematics course for first-year computer scientists that had, I guess, some quite easy proofs in it. I can't recall whether it was, I guess it did even try to teach a notion of formal proof using some kind of diagrams, but also it just had like some of the silly things you had to prove about, let's say, sets, really elementary things, which often baffled the students. I actually wrote a blog post called Most Proofs Are Trivial. I don't know if you saw it, but that insight really struck me, that most proofs are trivial. Certainly the ones that computer scientists tend to do in verification, they are often you're proving a program does the exact thing it was designed to do. And there's a lot of checking involved, but at no point is there anything that could be called an insight there. And even in a lot of the proofs that people work through in elementary mathematics courses, most of them, again, are turning a crank in a relatively straightforward way. And it is quite rare that you come up with a proof that needs something strange. And then some people object that say, why, I can't understand this proof. Well, yeah, it's a hard one. What was it? I forgot his name. Tim, last week, saying proofs need to be motivated. And they're not always, they're not always obvious. They're not always motivated. And those are the hard ones. Tim Gowers, yeah. Yeah, he said proofs need to be motivated, but no, they sometimes there's just some horrible thing you have to do, and then the result comes out. Or sometimes it's a really long calculation. Even a very long calculational proof Well, I guess it's hard to call that trivial if you're taking a thing and you're dividing it into n parts, and then you got this, and then you do something about a compactness and something. Then I guess it's an intricate proof, but even then there's often not really any insights in it. And I think these proofs can often be found by language models too, in fact, because it's just routine, a bag of techniques that people use.
I mean, some proofs might not be intricate, but they might just be extremely long. And you can break them
Long
into
and
very small
tiresome.
pieces.
Yeah.
I mean, but they can be gigantically long, right? And have lots of ideas. These are the things that I feel we're a long way from with AI.
Well, as I always say, it's the definitions that count. Like, oh God. It's that Chemeretti's something theorem that
Mm-hmm.
I forget the name. What is that Chemeretti's? What's the name of that theorem? It's just this it's this thing about large graphs, and the actual proof, there's nothing much to it. What is interesting is this notion of the energy of a graph or whatever it was. So he set up a bunch of definitions about graphs and the density and the energy and so on. And then he had the idea of proving this particular thing. The actual proof was, as I recall, a fairly straightforward induction when the genius came in setting up the definitions and the problem to begin with. And then, it's Chemeret's regularity theorem, isn't that what it's called? Realizing that this concept was useful. That was the genius. The actual proof was not particularly difficult. It's the definitions were where the genius lay. Right. And I don't see an LLM suddenly coming up with a system of idea. That's why I made the remark about conic sections earlier. Why should it be that a cone, as the Greeks conceived, why is that interesting? God knows.
Right. The graph of x squared add y squared is z squared, right? That's a fundamental equation that was
Well, but they didn't
all over
have
the place.
algebra. Like 3,000 years ago, they didn't have algebra. Why? How could they even conceive of these things and decide they should be studied? It baffles me.
Yeah. I was talking to somebody from Google about whether a computer could invent the concept of a group. And they said sort of the problem nowadays is that all the language models know what a group is and will never unknow it. So
Well,
we could no longer do that
Douglas,
experiment in some sense.
long ago, Douglas Lennet did a lot of work on mathematical discovery, he called it, like in the 1970s. I don't know if that ever attracted any attention. I mean, he went on to have a big career in AI, but not this sort of AI. I still think it is not a thing for computers yet.
Wonderful, thanks very much. We do have a few more questions, but I think we're running out of time, so it might be good for people to post those questions onto Zulip, and we can continue the discussion there. So I'd like to end the first day of this workshop by thanking the wonderful speakers we've had. Thank you so much, and all the attendees. And we very much look forward to seeing you tomorrow, which is 8 a.m. British Summer Time, for the second day of the workshop. Let's just give everyone a
Thank you.
Thank you. Bye-bye.
Bye.
Bye.